So we know that if we have a function that's continuous on a finite closed interval, it's going to have a max and a min. Our plan is to look for any critical points. Those are places where the derivative is 0 or undefined. We'll check each critical point in the function, each endpoint in the function. Whichever one has the largest output, that's got to be the max. Whichever one has the smallest output, that's got to be the min. So let's look at some examples of using this procedure. So we have this function. It's definitely a continuous function because it's a polynomial. And we have a closed finite interval, the interval from 1 to 6. So what we're going to do, remember our first step is to find all the critical points and check critical points and endpoints. So to find critical points are places where the derivative is 0. So I'm going to take the derivative. I can just use the product rule here. I'll take the derivative first times the second plus the first times the derivative of the second. Now, in this form, it's pretty easy to factor. I can pull out an x squared and 1x minus 5. So if I do that, if I pull an x squared, I have a 3 left behind and an x minus 5 left behind in the first term. In the second term, I have a 2 and an x left behind. So with just a little bit of collecting of like terms, I have this factored. We have 3x minus 15 plus 2x. So we have x squared, 3x plus 2x would be, so this is really 5x minus 15. I could pull a 5 out of that. If you pull a 5 out of 5x minus 15, you get x minus 3. So we have critical points at 0 and at 5 and at 3. So we have 3 critical points for this function. Now the endpoints are 1 and 6, so we're just going to evaluate the function at each of the critical points and at the endpoint. Now notice that 0 is not in the range. It's not between 1 and 6, so I can go ahead and leave that one out. But we'll evaluate the function at 1, and we'll find its value at 3, that's one of the critical points, and at 5, that's one of the critical points, and then at the right endpoint, which is 1. So plugging those into the original function, right? This is the function that we're talking about. If you plug in 1, you're going to have 1 cubed times 1 minus 5 squared. 1 minus 5 is negative 4. Negative 4 times itself is 16. 16 times 1 times 1 times 1 is 16. So f of 1 is 16. If you plug in 3, you have 3 cubed is 27. If you put a 3 here, 3 minus 5 is negative 2, and negative 2 squared is 4. So we have 4 times 27. Let's see, 4 times 25 would be 100 plus another 4 times 2 is another 8, so we have 108. And if we plug in 5, 5 minus 5 is 0, so the value of the function at 5 is actually 0. And if we plug in 6, plug in 6, 6 times 6 times 6 is 216. 6 minus 5 is 1, and 1 squared is 1, so we have 216 for the function. So we can see that the smallest value to come out is 0. So this is the min. Also, our max is 216. So if we look at this function, we know that the minimum value of 0 occurs when the input is 5, and so it occurs when x equals 5, and the maximum value of 216 occurs when x equals 6. So the max was on one of the boundaries, the min was at a critical point in the interior. And that's all you do, just find critical points and plug the critical points and endpoints into the function. Whichever one has the highest output must be the max. Whichever one has the lowest output must be the min. So you can figure out where the max and min occurs, so you can find out how to get the most or the least out of your function. Now in this example, I've removed the interval that this was defined on. So now we're talking about this function that's defined for all values x. So it's not over a finite closed interval. There may not be an absolute max and an absolute min. In fact, in this function there's not. Because if you were to multiply this out, you'd have x cubed times x squared would be the highest degree term. So this function is going to be x to the 5th plus lower order stuff, we'll call it. So when x is really large, x to the fifth is much larger than x to the fourth or any of the other powers that are down there. And so in the long run, when x is really large, we know the function's going to be acting like x to the fifth, which likes to go up as you move to the right and down as you move to the left. Now, so we can see then, because of the fact that this is a polynomial and it's going up to one side and down the other side, that there's going to be no highest value or lowest value, no absolute max or min. So no absolute extrema, in other words. The degree 5 polynomial, though, can turn up to 4 times, so it might have some wiggles in between here. And so at those wiggles, you could have a relative min, like I've drawn here, perhaps a relative max. Although it's also possible to have a spot where the derivative is 0, but then instead of going back down and making a max, then it could keep climbing, or it could be falling level and falling again, in which case we would have saddle points, we'd call them. So, oops, saddle points. Whereas this is a relative min, isn't it? Or a local min, and this is a relative max. So we know there's not an absolute max or an absolute min because this happens to be a polynomial of odd degree. But there still could be some relative max and relative mins. To find these, we could look for places where the derivative is 0 and then try to decide, once we found them, are they a max, a min, or perhaps a saddle. So we've already found the derivative of this function in the previous example, and we found that the derivative was 5x squared times x minus 5 times x minus 3, which meant that there were critical points at 0, 3, and 5. So we look at the number line and try to figure out what's going on. So we have this point at 0, and a point at 3, and a point at 5. We know at each of those the derivative is 0, so the function is actually level at those. Now we can look at what's happening before and after we get to these points. If you're at a max, it will be climbing, level, and then falling. And if you're at a min, it'll be falling, level, and then climbing. If you're at a saddle, you'll either be climbing, level, and climbing again, or falling, level, and falling again. So by analyzing what's happening with the derivative, we can decide which of these cases we're in. So let's look at on the other side of 0 here. Let's assume we're going to try an x value that's negative. Let's see what we can find out about the derivative. So if x is negative, x squared would be positive, and a negative number minus 5 is still negative, and a negative number minus 3 is still negative. So we have 5, which is positive, times a negative, times a negative. So that product would have to be positive, so we know here to the left of 0, y prime is greater than 0. Before we get to 0, it's climbing. Now between 0 and 3, we have a number that is still less than 3. This will be the product of two positive numbers, so the x squared will be positive times a positive, but this will be negative and this will be negative, so a positive times a positive times a negative is going to be positive. So after the 0, y prime is greater than 0 again. So if we know it's level at 0 because the derivative is 0 there, and we just figured out that before you get there it's climbing, and after you leave 0 it's climbing. So there must be a saddle at 0 because it's climbing, level, and then climbing again. If we look at between 3 and 5, if x is between 3 and 5, x minus 3 will be positive, but x minus 5 will be negative. So we'll have a positive times a negative times a positive times a positive times a positive. That's going to be negative. So between 3 and 5, the derivative is less than 0. So we know that the function is level at 3. It was climbing before we got there. Let's smooth this out a little bit. Climbing, level, and then falling. So there must be a relative max at 3. Now after 5, when x is more than 5, x minus 3 will be positive. More than 5 minus 5 will be positive, and more than 5 squared is obviously positive, so we have a product of a bunch of positive things. The derivative turns out to be positive. So we know that the function is level at 5, and it's falling before you get to 5, and we just found out that it's climbing after 5. So now we know that 0, if x equals 0, that's a saddle. x equals 3, we decided since it was climbing and then level and then falling, that would be a relative max. And at x equals 5, we were falling, then level, then climbing again. That would be a relative or local min for that function. Okay, before we had our function cut off between 1 and 6, and so we did have a lowest value when x was 5 and a highest value over here when x was 6, and some other critical points that turned out not to be an absolute max or min. Okay, so when you don't have restrictions on the domain, if you're not on a closed finite interval, then it's a little bit trickier to figure out what's going on. You may not even have an absolute max or an absolute min, for example.